So I'm Ferenc Hegedűs from the Budapest University of Technology and Economics from the Department of Hydrodynamic System. And now I would like to introduce you a program package which is capable to solve large number of independent ordinary differential equation systems. The first question is that how can we apply the massively parallel environment of GPUs for solving initial value problems, because an initial value problem is inherently serial. One possibility is to take a large number of instances of independent but identical ordinary differential equations with different parameters or with different initial conditions, and after that we can solve each instances or every instances in parallel. So what is the general form of the ordinary differential equation? We can see here. So x dot equal f x t p, where x is the vector of the state variables, t is time. It must be emphasized that every instances of an order system have its own time coordinates. So each instance has its own initial time t0 and its own final time t1. The dot stands for the derivative with respect to time, and p is the vector of the parameters. Now I distinguish three categories. The first one is the control parameters, which are different from instance to instance. The second type is shared parameters, which are common to all instances. And the last one is a special one. I call it accessories, which are user programmable parameters. I would like to highlight a little bit later that why it is useful. Now let us a short general overview of the capabilities of the program. It is written in C++ and it offers a framework to completely hide GPU programming. I try to keep the syntax as simple as possible to be able to use users who are new to C++ programming. A drawback is that so far there are only explicit solvers incorporated into the package, the force or the Runge-Kutta scheme and the adaptive Runge-Kutta cache-carp method. In addition, so far there is no option for dense output, but an efficient event handling is incorporated. Moreover, the user have the possibility to manipulate the trajectory after every successful time step or after every successful event detection. I will try to highlight that why it is useful in GPU programming. And the program package offers an easy way to distribute the workload to multiple GPUs. Let us discuss in more details about the implementation. The parallelization strategy is very simple. One GPU thread solves one instance of a system. So that's why we can use a very simple hierarchy of threads. We have one-dimensional grid with a one-dimensional block of threads or blocks of threads. The first task is to collect some basic information about the system. For instance, how many threads we would like to use, how many number of control parameters we have, how many shared parameters we have, and so on. We have to collect them in a built-in structure, a configuration structure, and with this structure we can initialize a so-called solver objects, as many as we want. These solver objects are responsible to integrate the system and for the data transfer between the host and the GPU side. And to each solver object we can assign a GPU device. So if we have any kind of GPU-related action, the solver object will automatically select the right device and perform the process in the specific device. Okay, how this process works in reality, here we can see a very simple code snippet. I set the number of threads to a certain number. And after that, I just collected the the important basic information which is related to how much memory we have to allocate on the CPU and the GPU side. So I had to specify the number of threads, the system dimension, how many control parameters we have, how many shared parameters we have, how many events we would like to detect, and how many accessories we have. These are the user programmable parameters. So after that, we can create the solver object. I have created here two solver objects, solver 1 and solver 2. And I specify the same device to each solver object. So both solver objects will use the same device. In this way, I can easily overlap kernel execution and memory transfer between the CPU and GPU side. For instance, while one solver performs integration, the other one can perform memory transactions. The next task is to fill up the solver object with data. It can be easily done with a member function called setHost. We have to specify the problem number, which is actually the serial number of the instances of the system. We have to specify the variable we have to set or would like to set. The possible options are time domain, actual state, which is the initial condition, actually, the control parameters, accessories, or shared parameters. After that, we have to specify the serial number. For instance, we have to set up we would like to set up the second control parameter. And finally, we have to specify the value we would like to set. In GPU programming, it is very important to have coalesced memory access. Fortunately, the user don't have to deal with such kind of problem. The setHost member function will place the value in the right place in the layout of the data. So therefore, I don't want to go into the details, so everything is handled by the solver object. Okay, how the code snippet look like? How can we fill up the solver object? Here we can see a very simple example. So we have a for cycle which just goes through the instances of the system, and with the successive call of the setHost member function, we can easily fill up the time domain, for instance, the initial condition and control parameters. The shared parameter is a little bit different because the shared parameters are shared among all the instances, so we have to specify them only once. So we have to specify only its serial number and the value. The next task is to set up the right-hand side of the system, the ODE function. Now it's a little bit tricky because to a kernel function we cannot pass a function pointer. So right now the program package works as follows. We have to specify the right-hand side in a dedicated device function placed in a specific header file. I know that it's a little bit inconvenient, but right now it's working like this. But nevertheless, we can specify the right-hand side very easily. It's very similar as in case of MATLAB. The only difference is that the indexing starts from 0. If you have an eagle eye, then you can recognize that this right-hand side is actually a single well Duffing oscillator. After that, we can perform the integration itself, but first we still have to specify some other parameters, like what are the block size, or what is the block size, what is the initial time step, or what kind of solver we want to use. And after that, this information have to be collected again in a pre-declared structure. And with this structure, we can call the solve member function, which performs the integration itself. For example, if we have a time periodic system and we would like to make some transient iteration, the only thing we have to do is to call successively the solve function within a for cycle. Let's imagine we perform transient iteration, and after that performing additional integration phases and save some data. We can accomplish some dynamical analysis. Now I would like to speak about in more details about the solver algorithm. If we call the solver member function, the first task it does is to load the shared variables, for instance, the shared parameters, into the shared memory of the device. After that, during an initialization process, the solver calls again a dedicated device function called initialization. It's very similar than the ODE function defined previously. The only difference is that it is called only once at the beginning of every integration phases. After that, we have to proceed the integration until we finish the integration process. That is, we reach the final time instance, or we stop the integration by an event. Okay, let's say that we have to perform the integration. We have to make a time step with a step pair and estimate the error. In this part, we have to call the ODE function introduced previously. If the step is rejected, then we have to approximate a better time step. If it is accepted, then we have to calculate a new time step, and let's proceed further with this branch. So after we estimated the new time step, the solver will evaluate the even function. Again, it's a dedicated device function. It's very similar as in case in MATLAB. And after that, we have to decide whether we successfully detected an event or not. If not, then we may have to adjust the time step to be able to find the event precisely. But if it is detected, then another dedicated device function will be called. The name is action after event detection. I will explain it a bit later, that's why it is important. And after the event handling process, the solver will call another dedicated device function called action after successful time step. After that, we have to update the state and continue the process until we successfully perform or completed the integration phase. And in the finalization, the solver again will call a dedicated device function called finalization. So why it is important to include these additional device functions? So first, let's imagine that we have to calculate, for instance, the largest Lyapunov exponent of a system. In this case, we have to linearize the system and attach it to the original one. And what we have to do after every integration phases is to normalize back the trajectory corresponding to the linear system to the unit circle. But how can we do that? If we have a CPU, we just simply integrate something, do the normalization, and continue the integration. But if we have a GPU, and if we would like to do that in a CPU, we have to copy back the final results, make the normalization, copy back into the GPU. But if we have the possibility to take any kind of action at the beginning of the integration phase or at the end of the integration phase, we can do this normalization easily. And if we have a time periodic system, then we don't have to copy back data to the CPU to do that. We can do it automatically, and with successfully calling the solver member function, we can do this normalization automatically. Another important thing, imagine that we have a non-smooth dynamical system, for instance, which can exhibit impact dynamics. What we have to do is to detect precisely with an event handling the impact. At the impact, we have to prescribe a certain impact law and reverse the velocity of the trajectory. How can we do that in MATLAB? We just integrate the system, detect the event, reverse, stop the integration, reverse the velocity of the body, and start again the integration. But it's not an efficient way in GPUs when we have thousands of threads, and what if just some parts of the thread detected the event. So it can result in a tremendous amount of threat divergence. So that's why it is important that we can take action after every successful event detection. If an event is detected, we can implement any kind of control logic inside this device function and just reverse the velocity of the body immediately, and all the threads can proceed further. Finally, why is it important to take action after every successful time step? I have mentioned previously that so far no dense output is supported. So what if we need a special property of a trajectory? For instance, the maximum of a certain component. What we can do is allocate a previously mentioned accessory, a user programmable parameter, initialize it with the initial condition, and after every successful time step, we have to check whether the new time step is bigger or the value is bigger than the previously stored, and just update it. So in this way, we can extract many features of the trajectories without the necessary to obtain a dense output and without the necessary to copy the lot of data corresponding to the dense output through the PCI Express bus to obtain this special feature using CPUs. So I would like to emphasize that this program package is not just a fast integrator. Rather than it's a tool to analyze a nonlinear system, the dynamics of nonlinear systems. Let me highlight these features through some examples. The first case study I want to show you is the Duffing oscillator, which is a second-order ordinary differential equation. Here P1 is the damping parameter, which is varied between 0.2 and 0.3, and it has a resolution of approximately 46,000. So altogether we have 46,000 instances of the Duffing oscillator, and we have approximately 46,000 threads. P2 is the excitation parameter, and the state space is periodic in time with periodicity 2 pi. So if we perform the integration many times and we have some transient iteration, and after that we proceed further and extract some features of the trajectories, then we can create a classical bifurcation diagram like this, where the first Poincare section of the first component is represented as a function of the control parameter. Here I used two NVIDIA Tesla K20 cards, and the total computation time was approximately 24 seconds. Another example I would like to show you is related to the Keller-Mixes equation, which is a second-order ordinary differential equation, and it describes the radial pulsation of a single spherical bubble. It's very important in sonochemistry because at the contraction phase, the temperature inside can be as high as several thousands of degrees of Kelvin, inducing chemical reactions. The problem here that with the conventional approach, using two harmonic components to the driving, we can end up with a relatively large parameter space. We have two amplitudes, two frequencies, and in general a phase shift between the components, and we have also an average bubble size. So the problem here is that we use only a moderate resolution of these parameters between 20 and 100, and we multiply them together, we can end up in approximately 2 billion parameter combinations. But using only two Tesla K20P, Tesla P100, it took only 23 days. So and finally, let me show you that how can we represent some results in a 6-dimensional parameter space. It's very interesting. So here you can see the chemical output of a single bubble in a 6-dimensional parameter space. One small contour plot means 2 dimensions. We can arrange them in a 2-dimensional structure, so we have 4 dimensions. And The other two parameters are varied in time, so we can have a global overview about the chemical output of a single bottle. I brought another example, case study, but I have no time, so I want to postpone it. So, in summary, the first version of the code is ready. It's already user-friendly and already capable of handling a large variety of problems. But we would like to extend it, for instance, to implement additional numerical schemes or the possibility of dense output and the possibility to solve delay differential equation. And the main goal of the next year is to implement efficient global and diffusional couplings of identical systems. If you are interested in my program code, please visit my website called www.gpod.com. And thank you very much for your attention.
So, any questions?
Do you need the first derivative to be explicitly expressed, or can it handle implicit problems?
Sorry, I didn't understand.
So when I solve the couple ODEs, do I have to express the first derivative equals to something?
Yeah.
Or can it actually do implicit problems when I have an algebraic equation which involves the first derivative?
No.
Any other questions?
Have you checked the efficiency of the implementation when you were running on the P100, whether it could be further optimized to reduce the execution time?
I haven't do that because I had a limited time to access these graphics cards, and my code is implemented in a Kepler architecture in a Titan Black graphics card, so I couldn't check it. But it's just a feeling, but it was approximately as fast as I expected compared to the peak theoretical power of the GPU.
And I wanted to ask, what was the particular reason you said that the user-provided function describing the system has to be a specific named function placed in a specific file? What was the constraint for that?
As far as I know, there is no possibility to make a function and play and just pass it as a function pointer to a kernel function. I don't know. Maybe in a later CUDA version it is possible, but.
I think you should check out the kernel lambda feature in CUDA, which serves this purpose, and then you don't need to have this restriction.
Okay. Thank you.
Any other questions? If not, then let's thank our speaker.